So when I was first asked to do this presentation, they said they're going to give me 45-minute slot, and then I figured out a couple of days ago I got 25 minutes. So it's going to be an action-packed session. Going to talk about two important features in the kind of recent Bluetooth specifications. And then if you have any questions, because this is going to be tight on time, I'm also going to be here for the Bluetooth panel right after this. So save your questions over there so we can get some discussion going on around these features. So as I said, my name is Mikko. I work for Silicon Labs. I run one commercial business at Silicon Labs. What commercial covers for us is commercial buildings, so any technology that goes into buildings like lighting, environmental sensing, access control. I also cover retail. We'll talk a little bit about electronic shelf labels. That's one application for Bluetooth in retail. I also cover asset tracking, automotive, and a bunch of other things. So briefly about Silicon Labs. If you don't know Silicon Labs, here's one slide intro. We are essentially a powerhouse for low-power IoT connectivity. Whether it's applications like electricity metering, gas, water, heat cost allocators, whether it's lighting in the residential space or commercial buildings, whether it's electronic shelf labels in the retail, we got you covered. If you look at our technology and portfolio for IoT connectivity, we cover 10 plus protocols ranging from Bluetooth, Zigbee, Matter to Wi-Fi, Wi-Sun, Amazon SiteWalk. So we're really, one-stop shop for most of your connectivity needs, if you will. So that's enough about Silicon Labs. Let's talk about one of the kind of the latest feature we introduced under the Bluetooth 6.0 standard called Bluetooth channel sounding. Let's do a little survey. Who knows channel sounding? If you know what it is, just raise your hand. We get a few hands over there, maybe less hands than I wanted to see, but after this session, all of you will know what Bluetooth channel sounding is. So why did we undertake the development of Bluetooth channel sounding at Bluetooth SIG? And the reason is, for many IoT applications, location awareness becomes a must-have thing or a nice-to-have thing. So, location awareness, we want to have it for convenience. I'm sure all of you know what Apple AirTags are, or similar tags from Google or Samsung. They help you to find your keys or wallets when they get lost. Super convenient, but it needs location awareness. For some other application, we want to have location awareness because of security. Imagine keyless entry for your cars. You want the car doors won't open unless you're 5 to 10 meters from your car. The car will not start unless the key is inside the car. It's there for convenience. It's there for security. The Bluetooth community has tried to solve the location problem, as long as Bluetooth's been out there. It started with Bluetooth Low Energy. It started with beaconing, RSSI monitoring, kind of location awareness, but it's not accurate. It's not reliable. Then we developed Bluetooth direction finding in one of the Bluetooth 5.1.5 specifications. Direction finding gives us a direction. The signal comes from that direction. But it doesn't straightforwardly give us distance. It just tells, the transmitter is over there. And then if you look at, what's out there in the market for distance measurement, ultra-wideband is kind of the de facto technology for distance measurement. It's used in AirTags. It's used in keyless entry for cars. It's part of access control door locks. But you need to add another radio. You need to add additional cost, additional complexity, additional certification. If you wanted that distance measurement capability, so you needed a Bluetooth radio for communication, ultra-wideband for distance measurement. So, because of these reasons, we undertook the development of Bluetooth channel sounding in the Bluetooth 6.0 standard. There's a need for connectivity because of convenience, because of security. We want to have accurate distance measurement between devices because some applications purely require that. And the community is always looking at how we can simplify things, how we can reduce power consumption, how we can reduce cost of these solutions so that they get more deployment. So we say, if we integrate distance measurement into Bluetooth, we can simplify a lot of these solutions and just have one radio in those devices. And that's what we went out to do. So with Bluetooth 6.0, we introduced Bluetooth channel sounding, which, very simply said, gives us accurate, secure distance measurement between two Bluetooth devices. So now you can say when you open a Bluetooth connection to your device, you know it's 5 meters away, 2 meters away, 3 meters away. You can add security to your application, or you can add location awareness to your application with a Bluetooth radio. Since this was developed under the Bluetooth kind of umbrella, one value promise we do, it's an interoperable standard technology. We've seen the first release of smartphones with this technology. I think the Google Pixel 10 is the first phone supporting this technology. We have technology showcases out there showing that phone works with our silicon, with some of the other silicon vendors out here. It's an interoperable technology. If you add it to your device, it will work with any smartphone or any other device out there that supports Bluetooth channel sounding. So that's the value promise of Bluetooth, which has always been the value promise, and it will still continue to be the value promise. And last but not least, when we talk about high security critical applications like keyless entry for cars, Bluetooth channel sounding adds a lot of enhanced security features for relay protection, replay protection, face manipulation protection, time manipulation protection, because that's, for example, what the automotive market requires. They don't want these wireless key fobs to be replicated and somebody nicking your cars because the technology is not secure. So that's one key part in addition to the pure distance measurement capabilities, high security. So let's talk about a little bit the use cases and target markets where we've seen this technology be adopted or starting to be adopted. And the obvious ones are kind of location-aware applications, residential door locks, commercial access control, especially when this technology goes out into the phones. You can start to use your phone as a key to your house, maybe as a key to your office, and we will see phones being used as keys to your cars as well. Geofencing, security alerts, again, something is in this room, it's nearby, we can trigger an alert. Somebody passed through the door, we can detect that and, do actions based on that. So that's kind of one group of applications where this technology is already being adopted. Then there's the kind of asset tracking, localization applications ranging from Apple Find My type attacks to more industrial commercial applications, tracking pallets, containers, other types of, more industrial commercial applications. And the third thing, which I didn't see coming when we started developing this technology, is actually mapping infrastructure. And this goes for, a good example is with the introduction of Wi-Fi 6 Enterprise and Wi-Fi 7. They added 6 gigahertz frequency to Wi-Fi. That brings a regulatory requirement that you need to be able to measure the distance between your Wi-Fi access points, because if they are too close, you need to reduce the transmit power on 6 gigahertz. You can't transmit at full power. So basically what all the Wi-Fi AP vendors are doing today, they're constantly measuring where their Wi-Fi access points are, putting them on a 2D floor plan. And if they get too close to each other because an IT guy installs a new Wi-Fi AP or moves an AP, they will automatically tune down the transmit power to be within the regulatory limits. And channel sounding is one technology which we can use to measure the distance between those access points and automatically build a 2D floor plan of where that infrastructure is without any or very little human interaction. And we've seen that same kind of use case work in other applications like commercial lighting. They want to understand where the luminaires are, place them on a floor plan. Today, it's all manual work. With technologies like this, we can automate it, we can reduce manual work, we can make it cheaper and more convenient to install. And there's many more applications, but these are some we've seen so far. So, with 25 minutes, we can't really dive into, deep down into how this technology works. But here's an overview of the capabilities we give you at kind of the low level. So, first of all, this is a connection-oriented technology. So whenever you want to do channel sounding, you need to establish a Bluetooth connection between the two devices. And why do we need this? Because we need to negotiate multiple things, and we need to synchronize clocks, and we need to understand how many antennas the devices have. So we need to exchange some data to understand, what is the device we are talking to and what are its capabilities. Once we've done that, we give you two methods to do channel sounding or distance measurement. The first and the simpler method is simple round-trip timing. So, the initiator device, like a smartphone, will send a message to the reflector device, and it will simply respond to that message. And then we measure the time difference that it took for that packet exchange. This is not a new technology. The challenge with round-trip time methods are always the clock accuracy on these devices. We don't want to put super accurate clocks on these devices because they're hard to get, they're expensive. But with the Bluetooth 6.0 standard, we are adding some additional timers into our Bluetooth radio to make the clocks more accurate and enable more accurate round-trip time measurements. And we're getting about 1 to 2 meters of accuracy with the round-trip time method, which is decent enough for some applications, but not everything. The other thing from security perspective, the round-trip time method gives us an additional security because it is very, very hard to manipulate time. So when we do the round-trip time measurement, it gives us coarse distance. Then we can move to the more accurate measurement, which is a phase-based measurement, where we transmit a phase signal, up to 72 channels over the Bluetooth bandwidth. The reflector is going to reflect that phase back to the initiator, and then we measure the phase distance, up to 72 channels, and that gives us accuracy down to 10, 20 centimeters, depending on the environment, the distance, the configuration. Do you have one antenna, two antennas, and so on and so on. But it can give us a very accurate distance. But it's a little bit more complex operation as we are transmitting more data, and we need to do more computation to get to that distance. So these are kind of the two toolboxes we give to you, depending what your application needs. If you only need simple distance, the RTT is a faster, lower power mechanism. If you need very accurate distance, you have a non-line of sight situation where multipath becomes a challenge. The phase-based measurement, can tackle most of those challenges because we just have more data we can work with. And then in the mode 3, as I said, you combine both measurements either for more accuracy, more security, or for other reasons. You can do a measurement where you do both measurements and then you correlate them between each other. So, in a simple things, that's how the technology works. But when you go into details, you have a lot of flexibility. You can decide how many antennas you put on the device, how often you do the measurement, how many channels do you use. So you have knobs between latency, accuracy, power consumption. You can optimize based on what the application needs are. So to summarize Bluetooth channel sounding, if you only have to remember one thing, this technology gives you distance measurement between two Bluetooth devices. The other thing, it's developed under the Bluetooth umbrella. It's standardized. If you develop a channel sounding product, it can be interoperable with other vendors' devices, smartphones, tablets, even automotive applications when we see this technology, being added to the cars. It simplifies things versus how we've done them today. How these, like how an Apple AirTag works today. There's a Bluetooth radio for data exchange and security setup. Ultra-wideband is used for distance measurement. With this technology, we can reduce cost, We can add more simplicity. We can reduce power consumption to make it more interesting and more easy to adopt technology for IoT. And last but not least, if you need that high security, if you're in the access control door lock space or keyless entry space, you have all those knobs for added security to make prevent or reduce the chance of somebody faking the distance measurement between your devices. Those are the key points for Bluetooth channel sounding. All right, the next topic, and I'm going to ask the audience the same. Who's heard about periodic advertising with responses, or PAwR? Again, a few hands raised up. So we got a lot of education we can do over here. So again, if there's only one thing you remember from this thing, PAwR enables low power, low latency, massive scale star networking. Something which wasn't possible with Bluetooth before the introduction of this technology in the 5.4 standard. So why did we develop periodic advertising with responses? Simply said, Bluetooth wasn't, we couldn't scale the technology to a massive scale star before. We can do point-to-point connections. Your phone can maybe connect to 5 to 6 devices at the same time. We do have the mesh topology, which is great for applications like lighting. But the market was demanding a massive scale, ultra low power, low latency star network topology. The lead application for this is something called an electronic shelf label. I'm sure if you've seen those in retail stores. They're essentially digital price tags which are replacing the paper labels in the store, and they're all wirelessly connected. And in this space, a lot of those companies who developed ESL, they had their own proprietary technology. How they did it, everybody had their own, no interoperability, and these companies had to invest a lot in developing their own proprietary technology, and especially during the allocation, semiconductor allocation, the retailers said, we don't want proprietary technologies, because these devices ship out in hundreds of millions of units a year. And the large retailers said, we want multiple suppliers for these labels. We want a standard technology, so we don't have a vendor lock-in with your proprietary solution. So those were the reasons why this development was kicked off under the Bluetooth umbrella. So we needed a new topology addressing massive scale star networking, and we needed an interoperable global standard solution instead of proprietary solutions. And there's always security is a key requirement. One requirement for developing this technology, we need to have a secure data exchange, with Bluetooth advertising, and this needs to be very low power, because these electronic shelf labels need to hit 5 to 10 years of lifetime, running coin cell batteries communicating every 2 seconds. So those were some of the reasons we developed this technology. And like said, I think everybody knows Bluetooth can do point-to-point connections. Everybody knows, you connect headphones to your phone. That's a point-to-point topology. We can send out Bluetooth advertisements, do RSSI measurements for kind of broadcast type applications. The challenge with that solution is it's one-way communications. It is not two-way communications, and it's asynchronous. So there's no synchronization between devices. So transmissions overlap. They lead to things like packet loss, additional transmissions, increased power consumption, and so on. And if you look at on the right-hand side, so the periodic advertising with responses, it's a two-way, kind of broadcast-based communication, but it's synchronous. So every device knows when they need to listen, when they need to transmit. So we can minimize overlaps. We can reduce power consumption by maximizing our sleep time. And it's two-way secure communication. So we can send sensitive data like pricing information over this communication, because it's all secured, with typical Bluetooth security methods. So a little bit on the technical details. So the Bluetooth 5.4 standard actually has two topics, or two things it covers. In the Bluetooth core specification, we introduced this communication topology called periodic advertising with responses, which enables that broadcast-based, two-way synchronized communication between Bluetooth devices. So, that's where the hard stuff happens. How do we, minimize power, maximize efficiency? And then the other part of the specification, which is very application-related or ESL application-related, is the ESL profile and service. So that's also part of the Bluetooth 5.4 standard. And the profile and service specification, they really define, how an application needs to work and, what kind of messages we send and, how do we build, interoperable devices at the application level. So the ESL profile and service, they tell you how do you update a new image to the ESL display and the price chains. How do you tell the display to actually change the image? How do you get sensor data from the displays or battery status, or how do you send some other commands to the devices? So that's really the application level communication specification, how these devices need to work. So how do we set up this massive scale star network PAwR? And as always, things always start with how do we set up the network? What's our communication frequency we need, and how many devices we need to have in the network? So you can impact a lot of parameters. Typically, you start the access point in the middle. It sets the communication frequency, like, I'm going to transmit once a second or 3 times a second or once a minute. And it will transfer those parameters to all the peripheral devices so that they will know exactly when they need to listen for any communication coming from the access point and when do they need to respond if they have something to say. So it always starts up by setting up the kind of the network operation mode, which really depends on the application net. Then the second thing we do is we need to figure out how do we want to group our devices. And there's a lot of flexibility there, but you can group your devices up to 128 groups, within that one access point. And the key thing over there is if you want to have a really large network of thousands of devices per access point, you need to have maybe a little bit less groups, so you can put more devices into a group. If you need to have a really low latency network where things communicate every 100 or a few hundred milliseconds, you might not want to group your devices differently. And you can get up to 255 devices in a group. And theoretically, these are always theoretical numbers, you can get up to 32,000 devices connected to one access point. In reality, to give you some real-life perspective, the largest networks we are doing with some of our partners today are about 7,000 nodes per access point. So pretty far from 32,000, but 7,000 low power synchronized nodes to one access point is still a pretty impressive number, in my opinion. And when you've set up your network, then you have something called the PAwR sub-event. How that works is in every sub-event, the whole communication starts by the access point sending a message to the whole group. So it sends a broadcast message, but we still have an addressing scheme, so the access point can send an individual message to an individual device in the group by using an addressing scheme. So, or you can send a broadcast message where you basically tell every device in the group, give me battery status, and then each of those devices, they have an individual response slot to basically reduce or minimize the chance of overlapping transmissions. And then, when the response slot comes, that's when the peripheral device can send a response back to the access point, like, my battery is at 50%. So, you can address individual devices, you can address the whole group, or you can address, parts of the devices in the group. So there's many message types depending on, what the application needs to do and what the requirements are. So A little bit complex, but I hope it gives you a rough idea, how do you set up a PAwR network and what capabilities you have over there. And this is the ESL profile and service specification. Like I told you, this is very electronic self-label specific, but it essentially tells you, how an electronic self-label, what kind of messages it can send to an access point, what are the types of messages the access point can send to an ESL, if connections drop or devices reset, how do they get back to the network? So this is what the service and profile specifications define, and that's one of the key things how we build interoperable solutions. So not going to jump into the details, but it gives you an idea that there's the lower level networking scheme part of the specification, and then this profile and service. This is very specific to how these electronic self-label devices work. So as a summary, the PAwR or Bluetooth 5.4, it gives us a new topology, massive scale star network with low power synchronized communications. This was something that wasn't possible before with this technology. Now it is. It was really driven to the standard by this electronic self-label market, but we are starting to see a lot of other applications where this topology makes sense. To give you an idea of one is we see like in large construction sites, we see a lot of charging devices. People bring their batteries to the charger. The charger can't charge all of them at the same time. So they're using PAwR to select which batteries are being charged and which need to wait until there's enough capacity to charge them. So there's other applications outside ESL where this topology makes sense. And with that, I think I'm out of time. I think we have the panel next, so if you have any questions, feel free to ask them during the panel discussion so we can continue the discussion there.